Thank you very much for the introduction, Tommy. And yeah, I work as an architect here in Giant Swarm. And currently, me and my team are focusing on stuff that is based around developer experience, which has a lot to do with how to manage applications on Kubernetes clusters. And that is exactly what I'm going to tell you about today. So agenda is standard and simple. I'll start with a short introduction to see what the problem is really about and why do we have to care about it actually. I will show you how our solution to this problem looks like, and then I will try to go a little bit deeper and show you not only what the solution is, but also how it works, and then a short summary and some ideas for the future if you're interested. So let's start with what is the problem and what we are going to talk about actually today. We want to deliver applications to Kubernetes clusters, where you run those clusters to run applications there, right? So you have to prepare those applications somehow. This means a few things before you can even get your deployment running. First of all, you need to figure out a few problems. How do you want to deliver your app in the first place? What machinery, what projects, what do you want to use to do that? How do you prepare this app according to this project, according to the solution that you've chosen? How to follow some best practices, how to make sure that the application that you prepare after actually deploying to a cluster will run and will run successfully. Finally, and this is like day one operations, what about day two? What about managing lifecycle, upgrading, deleting, moving, and so on? And also, how do you manage your configuration? Do you need some structured approach to your configuration? And over here in Giant Swarm, we are managing clusters for our customers, and we are offering basically a platform to create and manage your Kubernetes clusters. So we, together with our customers, we run hundreds of Kubernetes clusters. So these all problems are in a bit different light, okay, when you're seeing them at this scale. But still, like on a very basic level, you can say that, yeah, there are some tools that solve this problem already, and without a doubt, the golden standard and the most popular solution right now is called Helm, right? If you were using Kubernetes, you probably met Helm already, or you probably also used it. Helm is like a package manager for Kubernetes. So, you in Kubernetes, you have those different API objects like deployment, services, ingresses, network policies, whatever. You usually keep them as YAML manifests. What Helm allows you to do is to get all those manifests, all those objects that actually compose what you understand as a single application, and they allow you to combine it into a single package. And then there is some configuration. So this package is to some extent templated. So you can pass an external configuration to this package, and this configuration will be used as templating parameters so that the manifest that you have inside can get some external values. And all of that together, so the package and the configuration can be deployed to a Kubernetes cluster as a single management unit, which is already a big benefit, right? Because one important note, in Kubernetes, there's no concept of application, right? There are like namespaces, but this is definitely not an application. And then there are already like single deployments. There is nothing in between. And Helm like fits in between. Helm tries to define what is an application, a delivery unit. Just before we move on, let me just introduce three terminology words from Helm, because they have their own naming and it's hard to avoid them. So just very briefly, what Helm means by a chart is a package that can be installed to a cluster. Okay, so what you have packaged, your YAMLs, your templates packed into a single file. This is called a chart in Helm. A repository is just a remotely available storage that holds all the charts, and it is possible to download them from there. Simple as that. And the release is a chart that got its configuration and was deployed to a Kubernetes cluster. So it's a configured chart that is already deployed to a cluster. Okay, this can get pretty important because later we will be talking about charts and releases. So we need to start with some basics. So is Helm a solution? Yeah, definitely. To some extent, it is, because it solves some problems around packaging. It solves some problems around configuration and templating. But still, we have those problems, and now we have to solve them for all our clusters. Like I already said, it's something different when you have one or two clusters, and it's something very different if you have dozens or hundreds of them. And it turns out that when you want to apply your Helm as a tool, as it is, to multiple clusters, to fleets of clusters, more problems arise. And it turns out that Helm has a lot of shortcomings when talking about deployments at scale. First of all, there is no support for deploying to multiple clusters. So there is one-to-one relationship between a person configuring a Helm chart and the cluster where it gets deployed. Okay, so you basically need to target every single cluster separately. Next thing is that Helm is actually a delivery mechanism, but we need something more. We need also some tools to make sure that our charts can get tested properly before being delivered to a cluster. And well, there's not much support for that in Helm. Next thing, there's no representation in Kubernetes API. So Helm is using standard Kubernetes API objects and everything's fine with that. But Helm applications themselves, they are not represented in basically any way in Kubernetes API. So there is still no such object. There is discrepancy in how you can see your normal Kubernetes objects like deployments and services, and how you can see what you have installed with Helm. So there's no single pane of glass, no single way to manage that. And this is important once you start to integrate stuff with, like, let's say, CI/CD systems. Next limitation is there's only one configuration layer. So when you deploy, you give it full configuration. That's it. There is nothing like a default configuration that you can override or stuff like that, except for what is already embedded in the chart. Okay, but there's like no support for multi-layered configuration. And the last, although this time not really maybe that much important thing, is that a command that was used to deploy an application with Helm is usually just present in shell history of person that did the deployment, okay, or on logs on the CI/CD system. This is not ideal as well. So on one hand, we have Helm. Helm is like a golden standard. Helm solves some problems, but definitely doesn't solve all of them. So at Giant Swarm, we decided to create what we call an app platform. An app platform is a set of tools built around Helm. So we are not replacing Helm. We are extending Helm with some additional functionality that allows us to target the problems that you've seen. By doing that, we want to achieve a few things. First of all, we need to ensure build and release time quality. So we need to be able to follow our company's best practices around building Helm charts, no matter how many Helm charts we build, and we build hundreds. And we also need to have some tooling that will allow us to test application before we deliver the application to actual production clusters. We want to have a more consistent control about how it works, what it does, what is deployed where, and so on. Because of the whole integration idea and just having the cloud native feel to it, We want to have real Kubernetes API access to what is done by App Platform. And obviously, with this scale, we need to be able to somehow target multiple clusters from single point of control to make sure that everything is in sync and working the same, because, well, otherwise you can't really cope with it. So this is why. Now what? Basically, we can divide App Platform into separate tools that are strictly related to how we work on apps, and I will get to this in a moment. Currently, we have like 4 major steps in managing applications. First step is to create an app. So basically, how to take your sources, your YAML manifests, and turn them into a chart. Helm obviously has support for that, but we have extended this to somehow to make it more quality focused. And this is our create step. And we have a tool that is called App Build Suite for that. Next, before we even make this chart available, we want to test it. And we want to test it by running on a real Kubernetes cluster to make sure that everything works as expected. And hence, we have App Test Suite, which is responsible for this step. Then we have a delivery part, which is basically we need a storage. We need to put our charts somewhere so it is possible to download them and to use in any cluster we want. And then there is the biggest part, which is around manage, so basically lifecycle management and configuration management, where we have created our own Kubernetes operators that allow us to do what is necessary. And I will go deeper into each of those sub areas of App Platform to give you a better understanding and better explanation of what is what. And to do that, let me start with this chart. This is like a 10,000 meters view of App Platform without going into any details. The whole process of how we work on an application, from the source code, by source code I mean Helm chart source code, to deploying application to an actual cluster with its configuration, with lifecycle management tools and everything. We start on the left. So we as application developers have to prepare what is in blue on this chart. Orange is what we have created. So basically the tooling part of App Platform. Greenish thing is basically what we use from external sources, external projects. So we start with our chart sources. We add some metadata information to them, and then we pass that to our build tool. The build tool produces a Helm chart plus some extensions, optional extensions, so everything still works if you don't want them, that we call metadata. Metadata allows you to store some more information about the chart so that later you can take advantage of them and, for example, prevent your users from doing something potentially dangerous or just stupid that will result in application that is not usable because of some misconfiguration. At the second stage, when we already have a chart and we have a metadata, we provide tests. So we write different kinds of tests, and then we pass the chart under the build process and those tests to App Test Suite that takes an external Kubernetes cluster, deploys the chart there, and runs a test suite against them. If tests turn out green, we push the Helm chart and the related metadata to a Helm repository. So this is our storage. From there, we have operators that are running on management cluster. And here is an important assumption. If you are not our customer, we run our clusters and we manage our clusters always with a management cluster. So we have a dedicated management cluster that doesn't work any customer workloads, but that is used only for managing, observing, monitoring of workload clusters and a fleet of them. Okay, so this management cluster is now responsible for scanning remote Helm repository. We check what's there, we learn about the apps available, and then this is our control point. So operators come into this place and they declare which application should be deployed to which workload cluster. That's the 10,000 meters overview. And now let me try and go through this process step by step. So on a lower level, we'll have a peek, how it works, what it does, and what you can get from there. First part, building. Obviously, you can just build it. There's a Helm package command, and that's okay, right? But probably if you build your charts at scale, you have some best practices, you have some company policies, you have ways to follow, and you need to enforce them somehow, because otherwise people just won't remember to follow all the best practices. And for that purpose, we have built app build suite that I already mentioned. This is our opinionated and repeatable process that you can run as well on your development machine as in CI/CD. And the great thing is that you will get exactly the same experience and exactly the same feedback in both cases. All the tools that I'm talking here about are open source. So code is available, docs are available, you are free to go and give it a try. And our build process that is executed by app build suite roughly does the following. So it is taking care of setting versions. So it is integrated with Git. We always keep everything in Git. So we check versions from Git, tags, and so on. So we populate some metadata automatically. Chart YAML file is one of the files that stores metadata for a chart. Then we are reusing actually some publicly available open source linters and Helm chart quality tools. So we are not writing our own. We are just using what is available in the open source community and just orchestrating them into a pipeline that we can create over here. So we run those linters, we run Helm finally to package the chart after it passes all the quality checks. And in the end, we generate additional metadata because we support some additional one, so more than is just available in the chart YAML file. But this is, again, optional, so we are like 100% backward compatible with Helm. But if you want, you can get some extra functionality. And this metadata can include stuff like, is it possible to deploy this chart on a specific provider? So for example, you have clusters that have infrastructure provided by, let's say, AWS, but some others by Azure. Some apps make only sense if they are really running on, let's say, AWS clusters, and you can already enforce that. You can provide this metadata that, hey, this app really makes sense to be deployed only on AWS cluster. Or, for example, some other app can be deployed only once per cluster, and it is unsafe, or even everything will fail if you will deploy it multiple times. That's the case as well. Some of the metadata that we can provide and we can validate against. Obviously, if you are really adventurous, well, your clients can be your testers, but you probably shouldn't do that, right? So let's have a short peek at our test suite now, which takes the Helm chart that we built in the previous step, and with the similar approach, this is a tool that you can run on your dev machine and you can run also on your CI/CD instances, and it is oriented around scenarios. So this tool takes like two inputs, a chart to test and a set of tests to run against, and then it orchestrates those tests into what we call scenarios. And currently, scenarios are grouped into smoke, functional, and upgrade tests. I will show you how this works in more detail in a second. Currently, you can implement your tests in Python or Go. We have some helpers to do that. And we like the whole tool is responsible for just matching necessary tests to test scenarios and to your chart. Plus, it takes care of all the bootstrapping logic. So if you have a target cluster that is missing some app platform components that are necessary for the tests to work, it will bootstrap them. It will also make your chart available in the cluster, even though this chart is not yet released nor uploaded anywhere, and this will all work. So now about those test scenarios, because this is what is important. Currently, we have three scenarios, like I said already: smoke, functional, upgrade. And we execute those scenarios one by one. Smoke is obviously smoke test related stuff. So we follow fail fast principle. If you can only provide us a simple test that is very efficient at executing, but can already rule out some scenarios when the application will fail or is failing already, we can fail fast. So we avoid the overhead of running heavy tests, long-lasting tests, and everything, because we can first run and check if smoke tests pass. Then we run functional tests. Functional meaning your real application is deployed on a real Kubernetes cluster. Let's test the functionality of the app. Does it work? Does it do what it should be doing, right? And the last scenario that we support currently is the upgrade scenario, because upgrading is important part of a life cycle. We'll get to this later as well. But as you can imagine, it is easy to run into problems when you upgrade from one application to another, and there were some breaking changes that you missed, or basically anything. Upgrade is a tricky process sometimes, so it's really good to test this automatically. And in this case, our tool will first deploy the last known stable version of your application. Then it will do the upgrade and tell you what the results are. And from application tests developer point of view, the only thing that you need to provide is a set of tests, and then you need to mark those tests. So basically, which test will be run in which scenario. If it has a smoke mark, it will be obviously run in the smoke scenario. If it has functional and upgrade, it will be run for both of those scenarios, and so on and so on. So it's really easy because you implement your normal tests, and by just annotating them, the test suite already knows when to run which test and in which sequence. To make it even easier, we have developed a PyTest. So for Python, basically, people, a PyTest plugin that makes it even easier to write those tests. We have a set of helpers, set of dependency injected tools. So you don't even have to care about stuff like connecting to the cluster. When you use this plugin, you get ready connection to a cluster, ready full information about the cluster. You can easily check if your application works. You can easily connect to the application and so on. It is also part of our suite, and it is also obviously open source, so free to check it out. Next step on our journey, as you remember, is that once we have built the chart, tested the chart, now we have to store it somewhere, right? To be honest, so far we are not doing anything really sophisticated over here. We're keeping it as simple as possible. So our Helm repository is currently just served over HTTPS. So when you build a chart, you can generate also this index YAML file that Helm can maintain, and it will include all the information about applications and versions available. We are storing this on a normal web server. We are additionally uploading metadata information there that we got in the build and test step. And then our operators that already run on the clusters scan these repositories and update everything that is necessary on Kubernetes cluster side already. So now we get to the most sophisticated, probably, part of our platform, which is lifecycle management. Because, like I said, at this scale, we can't just install an application to a Kubernetes cluster. We need to have some tooling to make it reliable, repeatable, and, well, possible to control. So now we are focusing on our operators. And once again, we have this like double layout where we have a dedicated management cluster. This is our operational point. So this is our control plane. And a single management cluster can manage multiple workload clusters where your applications that we have prepared in previous steps can be deployed. So what tasks do we expect from our lifecycle management framework? First of all, we need to manage configuration. Like I already said, we need multiple configuration layers because we want to be able to do stuff like, let's provide our default configuration, but then let's provide something like customer-specific configuration. And then we might need to provide like a cluster-specific configuration, and still our end user might want to do some overrides. So we really need to have like some flexibility here to not always generate full configuration, but be able to do some local overrides. Obviously, we need some monitoring and status reporting because we need to know what is going on with our apps. And to make it a bit safer and easier for our users to manage, we want to do validation and defaulting for application management requests that are coming to the control plane. Once again, we are still over here 100% compatible with plain Helm charts and Helm registries. We are just building extensions on top, okay? And how those extensions look like. First of all, we have created cloud native, so Kubernetes native API to represent what Helm can do. So we have created 4 CRs that, and our users actually need to care mostly about 3 only and create only 2. First of them is catalog CR. Catalog custom resource is just an information for our operators. Where is a Helm registry? So it's basically a URL pointer. When this URL pointer is configured, our operators connect to this URL, scan the repository, and from this repository, they try to read all the applications and all the application versions that are available in the repository. Based on this information, they create what we call app catalog entry custom resource. So app catalog entry is an information about a single version of a single application. By querying app catalog entries, you can learn what is available in your catalogs. Now, this is, let's say, only information about apps available. So our next CR that we call app CR, app custom resource, is a request by an operator to deploy an application that is shown in app catalog entry to a specific remote cluster. So on a control plane, we create app CR, and this app CR tells which application should be deployed where. For better redundancy and isolation reasons, we have one more CR that is basically hidden from our users that is called chart CR. Chart CRs are created on target workload clusters, so on clusters where you want to deploy your applications, and they describe a configuration and an app that should be deployed to this cluster by just using Helm, okay? We'll get to this. This is just to make sure that the full information about what should be installed locally is present on the remote server, and not only on the control plane. So main software components that react to events and lifecycle of those custom resources are app operator, which is the most important operator that we have. What it does, it watches catalog CRs, so basically those CRs that answer the question, where are your catalogs? It watches for, it scans, like I said, those catalogs URLs to create app catalog entries, so information, Kubernetes native information for you about what is available in those catalogs, and also, by this way, what you can do with them or what you can install. It also watches, obviously, app CRs themselves. So this is the intent by the operator to deploy something and install something on a cluster. It does what we call a 3-level config merge. So our resources allow you to provide a configuration at 3 different levels, 3 different layers of configuration, or actually overlays. And it is responsible for merging them into the final version of the configuration. And also, it is responsible for creating chart CRs on target workload clusters. So on those clusters where your applications are ready to get deployed. The next operator that we have created is chart operator. It is much smaller. It runs on each workload cluster, so your target cluster, and basically watches for chart CRs that are created remotely by the management cluster and app operator running there. And chart CR, like I said, contains information about which Helm chart should be deployed where and using which configuration. So this is directly translated to Helm operations, local Helm operations on this cluster. We have 2 more support components that are called App Admission Controller and App Exporter. App Admission Controller runs back on management cluster only, and it is our validation and admission framework, let's say. So like I said, we are collecting a lot of metadata, like the example that I gave. You can only have 1 instance of this application deployed per each cluster. So we need to and we can enforce it, having this metadata info. and you can use app admission controller to do that. So you can make your installation and management process less error prone and easier for your users because we have this component. And finally, app exporter, which runs on management clusters as well. This is our monitoring extension that scans constantly for app CRs present at local management cluster and reports some statistics in Prometheus format for us to be able to monitor and to alert about application lifecycle management events. Okay, so we have the components I have just described, but the actual deployment process is a little bit more complex. So let me give you a complete example and let me go step by step over here so we can better see what is going on for lifecycle management. So we are going really deeper into app platform now. So once again, we have a management cluster. Our only point of interaction with operators for the whole fleet of clusters that you have. We have a reserved namespace, and in this reserved namespace, we run our lifecycle management part of app platform components. So the two operators that I mentioned, monitoring support component and admission component. Now, for each target cluster, so a workload cluster that we want to manage with app platform, we create a separate namespace. This is like a good organizational practice that you don't want to put everything in a single bag, right? It will be hard to tell what is going where. So we are distinguishing them by namespaces. So in this case, we have a cluster that is named Cafe1, and this is a namespace that is created for managing this cluster. Over there, by kubectl or any other way that you can interact with your Kubernetes cluster, an operator can create app CR or catalog CR, and they will be picked by and operated by a dedicated app operator instance for this cluster. So yes, we have dedicated instances to keep better isolation. Our master clusters, so management clusters, are heavily multi-tenant, and we care about multi-tenant isolation. So that is also why you get a dedicated instance of app operator to process configuration, because configuration includes secrets and such things. So we have a dedicated instance for each cluster, so there's like no cross-cluster potential contamination of some secrets, let's say, passwords, stuff like that. So now the whole process starts by an operator creating a catalog CR that you can see here on the left, and app operator reacts to this event, and as a result, it creates ACEs, so app catalog entries, scans the catalog, checks which applications in which versions are available, and creates ACEs. Now the operator can list them, so can check what is available, which apps, which versions, and make a call what should be deployed where. This intent of what should be deployed where is described by appcr. So appcr says deploy application X, let's say Nginx, in version 2.5.1 to a remote cluster that is called Cafe1. Okay, this appcr is created, app operator picks it up and connects to the remote Cafe1 cluster, where we also have a dedicated namespace for our tools, and creates a chart CR over there. This chart CR is now picked up by chart operator, our component that scans and watches chart CRs all the time. This operator, in turn, uses Helm. So like I said, we are always Helm compatible. So it uses Helm to create a Helm release. And Helm release is now given the chart, full configuration after all the templating, 3-layer merge, and so on, and deploys everything what you have included in your app, like your deployments, your services, and so on. Obviously, this can be done for multiple clusters. So if you have another cluster called Cafe2, this looks like a copy-paste diagram, because it is. And you have just a different cluster over here. Components are duplicated and everything works the same. You can manage multiple clusters using the same information from a single operational control point. Okay, now one thing I didn't mention already actually in the introduction, but still I want to just show you one thing, share one thought. Even though we have all of those mechanics, so we have management cluster, on management cluster we have AppCR, we have related config maps that hold the configuration. In some cases, like unfortunately disaster recovery, we need to have better information about what was done to that cluster. So you want to recover a cluster, you want to know what is the last configuration applied to an application, but your cluster is not responding, and the person that had actual configuration files on his or her laptop is not available right now. Obviously, that's not acceptable. And right now, we are heavily working on integrating and providing best practices for integrating our app platform with GitOps-based solutions. And we already have this like pretty much ready. We are polishing some stuff out right now. But the idea that I want to show you and I want to share with you is that because right now everything we do to manage our applications is just create normal Kubernetes API resources, in this case custom resources, but still you manage them the same way. The integration with GitOps tools is natural. So GitOps tools, they usually take a Git repository where you have your YAML manifest, and then those manifests are deployed to your Git repository, to your cluster, and synchronized between them, right? So everything you need to do to make sure that your apps and their configuration is always represented and the only source of truth is the Git repository is to put them into repository as YAML manifests. That's it, because the configuration interface is now consistent. Just remember that when you put stuff into a repository, you can't put plain text secrets. That would be dangerous. There are some tools that you can use to solve this problem. Currently, because we have focused on Flux and we use Flux as our GitOps system, we are using a tool called SOPs currently that allows you to encrypt everything that goes into the repository with a public key, when the private key is only available on the cluster, and only there your secrets can be decrypted and applied to a cluster. Okay, so that is everything I have prepared for you for today. Let me summarize quickly. We at Giant Swarm manage hundreds of clusters, and we need to deliver apps to them constantly and many, and we need to make sure that those apps work and have sufficient quality. Helm is a de facto standard for managing application packages for Kubernetes, still has so many shortcomings when you talk about delivering apps at scale, that we decided to enhance Helm and build a set of tools around it that we call App Platform. In this App Platform, we are targeting the full developer experience. So we are starting from building charts and testing them, storing them, and the most important and the most sophisticated part of it, so lifecycle management. Now we are also integrating, and like I said, we are basically almost done, a good GitOps experience, because this is a natural extension and a perfect natural integration between them. And that way we can really manage our infrastructure, all the apps deployed at the scale that we have over here. Is the story complete? Obviously, it's not. There are always more improvements, more ideas for the future. Some things that we definitely want to include now in the app platform is an also opinionated, enforced delivery pipeline security. Right now, we are handling security, obviously, but we are doing that at different stages that are not really integrated with a platform. We would like to have a common shared experience. And also, we find very interesting and very profitable this idea of enhanced metadata. So for example, we would like to introduce real Kubernetes compatibility testing, so not just by declaration, but we would like to actually run our apps on different Kubernetes clusters and save information if they were running successfully on this specific Kubernetes release or not. And what is really missing, but it is a hard topic, is how to handle real dynamic application dependencies. So how to figure out that I can't install my application Y on a target cluster because some other application X is not yet installed and is a dependency for application Y.